sounds good. And
have a look.
Yeah, I'm on the YouTube page now. I can't see any streaming.
No, it takes about 20 seconds before that actually kicks in.
Okay, yeah.
It's
looks
going
like
now.
it's going now. Yeah. Yeah, I can see you. Yes.
Okay. So the only thing, could I just ask, is the speaker for the second talk here?
Yeah, I'll stop the YouTube window since it echoes.
Yeah, turn the sound off on it. Or
Okay.
Yeah,
I just switch it off completely.
I
So I think we are probably about ready now.
Yeah, I'll try and right. Is Sasano? Are you the second speaker, Sasano?
Hello, yes, I am the speaker of the second talk.
Okay, great.
Yeah.
Great. Okay, Torben, you take it away.
So, okay, thank you. So, welcome to PEPM 2021, and I admit this is the first time I've tried a setup like this with all these different software systems, but I hope we'll figure it out in common. You who are on Zoom, you can use the chat to ask questions. If you want to ask a questions about something that's being said at the moment, then just write a star in the chat forum, and then I can stop the speaker and you can ask your question, unmute yourself, and then ask your question. And if it's something that can wait until later, we can just have a session at the end where you can just mark again, and then you can ask then I'll unmute you and you can ask your question. Let's see how it works out. I expect it will be okay. So the speaker will get 25 minutes and then we'll have questions. If there are a lot of questions during the talk, we will probably extend the actual talk time to counter for that. And I hope that will work out. So the first paper is called A Functional Abstraction of Type Trails, and it's by Kenichi, Asai, Youyou, Cong, and Chiaki, Ishio, and they are all from different universities in Japan, as far as I can see, and the paper will be presented by Youyou Cong, so please go ahead.
Yes, thank you. So let me share my screen. Is everything okay? Okay, perfect.
Looks fine from here.
Okay, so hi everyone, I'm Youyou. My talk is about designing a type system for a variant of the limited control operators. This is joint work with my colleagues Kenichi and Chiaki at Autonomous University. The limited continuations are something the programming languages researchers have been loving for decades. They're useful in many ways. We can use them to express various effects, represent monads in direct style, and implement partial evaluation, which is one of the main topics of this workshop. As a tool for handling the limited continuations, algebraic effects and handlers are becoming more and more popular, but a more traditional tool is control operators. There are many different kinds of control operators in the literature. Some of them, such as shift and reset by Dombey and Filinsky, are well studied, but several variants still don't have a type system that is said to be canonical. This prevents us from understanding their semantics and making a comparison between different kinds of control operators. The long-term goal of our research is to formalize all variants of delimited control operators. In this talk, I'm going to discuss one particular variant called control and prompt. These operators are classified as dynamic in that they do not allow us to statically determine the extent of captured continuations. This dynamic behavior has an interesting use case, namely breadth-first traversal, but it also makes it hard to type programs. So our contribution is to identify all the typing constraints that arise from the dynamic behavior of control and prompt. Let's look at an example and see how control and prompt work. Here, I write F to mean control and brackets to mean prompt. And we are using two primitive functions. If0 tells us whether a given integer is 0 or not, and B2S converts a Boolean into a string value, true or false. Assuming a call by value left to right evaluation strategy, we first evaluate the control operator on the left. This control operator captures the addition context enclosed by the prompt. Then it binds the variable k1 to the refied continuation and evaluates the body, which invokes k1 in an is0 context. After beta reducing the application of k1, we get another control operator in the evaluation position. And this is the place where an interesting thing happens. So this second control captures the addition context, which was originally surrounding itself, plus the is0 function, which was surrounding the invocation of k1. This happens because a continuation captured by control is not surrounded by a prompt. In fact, if we replace control with shift, then this capturing of is0 would not happen because every continuation is surrounded by a reset. Back to our example, we capture this continuation and evaluate the body of the second control, which invokes K2 in a B2S context. After beta reducing the application of K2, we obtain an nested expression that looks like this. So here we see that the original delimited context and the invocation context of the first continuation and the invocation context of the second continuation are all composed together. And after that, we obtain the string false. From this example, we can make two observations. First, control can capture the invocation context of previously captured continuations. This means a captured continuation consists of a delimited context and a trail of invocation context. Secondly, this trail of invocation context can be heterogeneous. In our particular example, we call this first continuation into bool context, whereas the second continuation is called in bool to string context. These types are apparently different, and for each of them, the input and output types are also different. Unfortunately, our example would be rejected by the existing type system for control and prompt. The reason is that the type system requires all the invocation context within a prompt clause to have the same type, and for each of them, the input and output types must also be equal. What we would like to do is to remove all these constraints on trail types so that we can accept our example as a well-typed program. How do we do that? Our idea is twofold. Typically, a type system for delimited control operators is derived from a CPS translation. For control and prompt, there exist two kinds of CPS translation. One of them treats a trail as a list of contexts, whereas the other one treats a trail as a function. We find that if we adopt a functional representation of trails and really carefully analyze the CPS translation, then we can build a type system that is more flexible about the type of trails. To design a type system, we have to first identify the right form of typing judgment according to the CPS translation. An expression that uses control and prompt is CPS translated to a function that takes in a continuation K and a trail T, which contains all the invocation context within a prompt clause. In the general case, we can type the translated expression like this. There are three things to observe here. First, a continuation now takes in a value and a trail. This reflects the fact that a continuation requires a number of invocation contexts to complete its computation. Secondly, unlike the CPS translation of pure expressions, the return type of the continuation and the type of the final value can be different. This is a common feature shared among delimited control operators, and it is known as answer type modification in the literature. And lastly, we see that the type of the trail required by E and the type of the trail required by its continuation can also be different. This is unique to control and prompt, and by analogy, we call this trail type modification. A typing judgment, then, has to explicitly carry all these 5 types. So here, the first 3 types correspond to the continuation, and the next one represents the type of the trail required by E. And the last type tells us what kind of value we get after evaluation of E. In this talk, we are going to focus on what kind of trail type we can assign to expressions. And for convenience, we call mu beta initial trail type and mu alpha final trail type. So now we have a typing judgment, but we haven't seen what kind of type we give to trails. In our CPS translation, an empty trail is represented as unit, and a non-empty trail is represented as a function. In the latter case, we use an arrow type with 2 inputs. That is, we type a trail just as we type a continuation. And when a non-empty trail is given this arrow type, it means the trail accepts a value of type tau, and in the future, it will be composed with a trail of type mu, and after this composition, it returns a value of type tau prime. So we can see that our trail type is explicit about the future extension. And an interesting fact is that if we represent trails as lists in the CPS translation, then it will be tricky to give this kind of precise types to trails. And this is why the previous work restricts trails to be homogeneous. Okay, with this in mind, we define the typing rules for control and prompt. So we begin with the prompt case. Prompt is something that delimits the extent of the relevant computation. In CPS translation, this is described as running the CPS of E with the identity continuation and an empty trail. It is not hard to see that for this translation to be well typed, the initial trail type of E must be the bullet type, which represents the empty trail type. But what about the type of the continuation? We have to make sure that this type is consistent with the identity continuation. In our type system, we use a relation isId trail to encode the constraints imposed by the application of E to KID. And the definition of this isId trail relation is derived from the definition of the identity continuation. The identity continuation here is not the identity function. It takes in a value v and a trail t and behaves differently depending on whether t is empty or not. When t is empty, the identity continuation simply returns the value v. From a typing perspective, this means the type of v and the return type of the case analysis must be the same. Therefore, in the definition of isId trail, we say when muid is empty, the two types beta and beta prime must be equal. Now suppose t is non-empty. In this case, it must be a function representing an invocation context. And we call this function with the value v and an empty trail. From this application, we can deduce that the function k must accept a value of type beta and a trail of type bullet and return a value of type beta prime. Therefore, in the isId trail relation, we say when id is a non-empty trail type, the first and third types must be beta and beta prime, and the second type must be bullet. Now we have defined this isId trail relation, and using that, we define the typing rule of prompt. In the premise, these three types comes from the continuation of E, which are guaranteed to be consistent with the identity continuation thanks to the isId trail relation. And we have this bullet type as the initial trail type for E, meaning that it is type safe to delimit the context of E. In the conclusion, we see that the two trail types and the two answer types are both equal. This means a prompt expression is a pure expression that does not change the answer type or trail type. This is how we type prompt, and we next look at the control case. Here is the CPS translation. We see that we are again running the CPS of E with the identity continuation and the empty trail. And what is new here is this substitution, which involves extension of trails. To make things easier to read, we are using list notations on trails, but this append and cons are actually defined as function composition, and our main task here is to ensure that this composition is type safe. In our type system, we use a compatibility relation to ensure this type safety. This relation says, when we compose a context of type mu1 and another context of type mu2, we get a context of type mu3. Intuitively, we are defining an addition over trail types, and its definition is derived from the definition of append and cons. Here's how append is defined. The append operation takes in two trails, T and T prime, and pattern matches on T. When T is empty, the result of append is T prime. From this, we can derive the first clause for addition, which says bullet plus something is something. When T is non-empty, the definition refers to the cons operation, so we have to look at how cons is defined. Here's the definition. The cons operation takes in a continuation K and a trail T, and pattern matches on T. When T is empty, the result of cons is the first argument K. From this, we obtain the second clause for addition, which is again straightforward. When T is non-empty, on the other hand, things are quite complicated. I'm not going to explain all the details here, but the main point is that since the definition of cons has a recursive call, the definition of addition should also have a recursive call. And by incorporating the constraints that imposed by the application of K to V, we can derive this third clause for the addition. So now we have defined this addition for the compatibility relation, and using that, we can define the typing rule for control. As in the prompt case, we have this isId trail relation constraining the type of the continuation of E. And we have an empty initial trail type for E, which means it is type safe to evaluate E within a prompt clause. And in addition to those, we have two compatibility relations. The first one says, consing K prime to T prime is type safe, and the result has type mu0. And the second one says, appending T to the result of cons is also type safe, and the result has type mu alpha as required by the continuation K. In the conclusion, we see that the true trail types and the two answer types are both different. And in particular, the final trail type, mu alpha, represents the trail after the cons and append operation. So using this compatibility relation, our type system can see whether a program manipulates context in a type-safe way. And as a consequence, we can now accept our example as a well-typed program. Let me show you how the type of the trail is updated as evaluation goes. Before evaluating the body of prompt, the trail type is empty because there's nothing in the trail. After evaluating the first control, the trail type is updated to this arrow type. The first type is the input type of the innermost invocation context, which in our case is the is0 function. The second type is the type of the context to be composed in the future. In our example, this future context is the B2S function, so we have this Bluetooth string type here. And the last type is the output type of the future context, which is string. So this is the final trail type of the first control. And if we use this trail to evaluate the second control, we will obtain a new trail of this simpler type. So we find that the trail type in the middle has been discharged. This is because we have composed the B2S function as required by the previous trail. At the level of types, this discharging is the result of adding the previous trail type and the type of the B2S function. By this kind of reasoning, we can conclude that the whole program is well-typed. Okay, so we have proved a few good properties of our type system. Among these, termination is unique to our calculus. In the previous type system for control and prompt, one can write terminating and well-typed programs. We are currently trying to prove the correctness of the CPS translation, which is a slight modification of Kenshan's translation. And we are also looking for practical application of heterogeneous trails. So if you have any ideas on this, we'd love to hear. To summarize, I have shown how to design a general type system for control prompt. The key is to closely analyze the CPS translation while adopting a functional representation of trails. There's an ACTA implementation of our type system on GitHub, so if you are interested, please visit our repository. Thank you.
Thank you. So do anyone have questions? You can either use the raise hand. Yeah, Julia Laval has a question. So please, you can unmute yourself and ask the question.
Okay, hello.
Hi.
So my question is, I mean, your motivating example seems a little bit strange because in many languages, there's no order of evaluation forced on plus, the two arguments of plus. So that particular program doesn't make sense if you take the right to left evaluation. But I guess your example would work out exactly the same. I mean, it would continue to fail in the previous type system if you had done something more sensible somehow with like let, and then the first argument, and then let v equal be the first argument, and then v plus the second argument.
Okay, so I think when you incorporate this kind of control filters into a programming language, then you have to force the evaluation order in some way. So yeah.
I was wondering if you could adjust your type system so that in the plus case, it would force any continuations to have the same return type. But in the more sequential, explicitly sequential case, it would have the flexibility that you offer.
So let me ask my co-author. Kenichi, do you want to say something?
Yes. Well, if you have any control operators, then you have to define the evaluation order anyway. So even if you don't have any control operators, say you have exceptions. If you say raise A plus raise B, then do we get an exception of A or exception of B? And to determine that, you need the evaluation order anyway. So I don't think you can specify a rule that goes well for the that goes both ways for the plus, simply writing plus, and sophisticated way in the let expression. I don't think that's possible.
Okay, but I mean, I don't completely agree because I mean, in your example, you're talking about evaluation, and here we're talking about type inference. So if you had raise 3 plus raise 4, okay, it's non-deterministic, but at least the types still work out. It's always integer.
Uh-huh.
But
So-
Well,
oh, sorry. So in the presence of the limited control, like the original type system of shift and reset by Domi and Felinsky, are also sensitive to evaluation order. I think this is pretty a normal thing in limited control calculus.
And yes, well, you might be able to impose more stricter constraints on the types so that you might be able to get one. So for the specific plus operator, then if you don't want to impose any evaluation order, then I think you have to impose more typing constraints to that. And if you are okay with that, then you might be able to define such a thing, I would think.
Okay, thank you.
Yeah, any further questions? I wrote a comment in the chat forum saying that since you consider addition to be sequential, then instead of taking a pair of integers as an argument, you could maybe query it to make it explicit that it takes one argument at a time.
Let's see.
Yeah.
But even if we accept a pair of integers, we have to decide which integer to evaluate first, no?
Yeah. So it's all down to an operational semantics, which we haven't seen yet. But yeah, any further questions? Otherwise, I think we should move on to the next speaker and thank the current speaker. Doesn't seem to be any more questions. So thank you for your talk. And let's move on to the next paper, which is called A Text-Based Syntax Completion Method Using LR Parsing. And it's presented by Isao Sasano and Kwanghoon Choi. I apologize about pronunciation of these names, but who is the actual speaker?
I am the speaker.
Okay.
Isao Sasano.
Yeah. So just yeah. So that's Isao Sasano. So just go ahead and give your presentation.
Okay, I start the presentation. I am Isao Sasano from Shibaura Institute of Technology, Japan. This is a collaboration with Kwanghoon Choi from Cheonnan National University in Korea. The topic is about syntax completion on editors. And many integrated development environments provide syntax completion functionality. And developers of IDEs have to implement features like syntax-aware editing for each language. And in 1980s, structured editors or projectional editors like synthesizer generator or Mentor was developed. In these editors, behaviors of functionalities are formally specified, and they easily support syntax-aware editing. But structured editors prevent programmers from freely editing text, except for the editors produced by LLC system. I mentioned this system later. The objective of this work is to propose an algorithm for generating syntax completion functionality from a given grammar of some language. And the proposing algorithm uses the internal information of the LR parser. let's see an example of our tool. The program is written in standard ML language, and this is called a let expression. Let expression. Oh, my face was not displayed. Okay. This is a let expression in the middle of inputting let expression. And then in the cursor position, the user may type a tab key, and then two candidates are popped up in this case. Well, let's see another example. This example completes parenthesized expressions. This is again a standard ML language. This is a partial function expression, and the body is a partial input nested function call expression. There are 4 function calls and 3 open parentheses not yet closed. Then there are 3 candidates popped up. 1 closed parenthesis, 2 closed parentheses, and 3 closed parentheses. So we have designed this kind of algorithms and implemented. Then, in order to provide this kind of functionality, we have to consider how to specify the not yet input program portion. We formally specify the remaining part, not yet input, of the program after the cursor position by using the grammar of the target language. And we ignore the text after the cursor position if there is any text. Then, firstly, we introduce a notion about postfix sentential forms. This is our new notion by using a sentential form. A sentential form is a sequence of symbols that can, sequence of symbols that can be derived from the start symbol in the grammar. This is a well-known thing. Then let alpha be the sequence of terminal or non-terminal symbols. Here is alpha. And when alpha beta, concatenation of alpha beta is a sentential form, we refer to the sequence beta, this part, beta, as a postfix sentential form with respect to alpha. And here is the cursor position. So we introduce this notion. And there are, in general, infinitely many postfix sentential forms for given sequence alpha. Then the candidates that are expected to be completed by the programmers are those which correspond to or close some of the syntactic components in the program text up to the cursor position. So this is the intuitive explanation of the candidates. Then this is our idea. This intuitive notion can be captured by the concept of reduction in error parsing. This is our idea. Based on this idea, we first represent simple candidates. And later, we define another candidates called nested candidates by using simple candidates, by combining simple candidates. Then, okay, so this figure, this diagram represents the notion of simple candidates. S is the start symbol of the grammar. And alpha, let alpha be a prefix of a sentential form. So this whole part is a sentential form. And alpha is a prefix of this sentential form. And intuitively speaking, alpha is a symbol on the stack when the LR parser parsed the code up to the cursor. This is the intuitive meaning of the alpha. But this definition itself doesn't concern the LR parser. Then, a sequence of terminal or non-terminal symbols gamma is depicted here, is a simple candidate with respect to alpha when this diagram holds. So there may be some symbols here. So the concatenation of alpha, gamma, and this part is a sentential form. Then, as I said, some part around here must be a right-hand side of some production of the grammar. So suppose one production in the grammar is a arrow, some symbol, some sequence of symbols. Then this part must appear around here. Then the condition is this one. The length of the sequence RHS must be greater than the length of gamma here. This is the condition. Then we say gamma is a simple candidate with respect to alpha. Okay. Then let's see an example. This is a simple arithmetic language. The start symbol is E in this case. So E may be A, or E plus A, or E minus A. Then A may be a number or a parenthesized expression. Then suppose the programmer have typed open parenthesis 2 plus 3, and here is the cursor. Then in this situation, there are three simple candidates according to the specification in the previous slide. Plus A, minus A, and close parentheses. There are these three simple candidates, and there are no other simple candidates in this situation. I don't explain in detail, but these three satisfies the specification in the previous slide. And this is a screenshot of the two. And here is 3 dots. In our implementation, we replace all occurrences of non-terminal symbols in the candidates with 3 dots, like this way. Then, so this is not an essential thing. Then, let's see another example. This is a subset of a standard ML language, a very small subset. And let's suppose the programmer have typed up to here. So this is the partial let expression, and here is the cursor. In this case, there is only one simple candidate, EXP. EXP is the only simple candidate in this case, according to the specification. Please see this part. EXP may be FNID double arrow EXP. So the candidate EXP corresponds to the occurrence EXP inside this function expression. So by inputting EXP, this part, FNX double arrow EXP, it becomes the right-hand side of a production here, EXP arrow this sequence. So EXP becomes a simple candidate. And in this case, there are no other simple candidate. But so usual programmer may expect in or end in the candidates to be popped up because this whole expression is a partial let expression actually. And a let expression is this one. Let a declaration in EXP end. So there are keywords in and end here. So a programmer may expect this kind of keywords, but the simple candidate is just this one, EXP. So we'd like to extend the candidates to include in and end in this case. Then, so we introduce nested candidates. Nested candidate is defined by this diagram. Roughly speaking, this one just repeats simple candidates many times, like this way, by starting with the start symbol S. Start symbol S here until the target sequence, in this case alpha 0. This one is a result of the parsing up to the cursor, roughly speaking. So up to this sequence alpha 0 appears. So in general, we have to expand a non-terminal symbol many times until we obtain this kind of sequence. Then you can see gamma 0, gamma 1, and so on. So gamma 0, gamma 1, and so on are simple candidates for each sequence, roughly speaking. Then let's see the previous example again in standard ML. Let var hat equals fnx double r. Here is the cursor. So there was only one simple candidate, exp, in this case. And by extending to the nested candidates, there are two nested candidates. One is exp. It was the simple candidate. And there is another candidate, exp in, exp end. Then I roughly explain by this diagram. Starting from the start symbol, in this case start, we repeatedly expand some non-terminal symbol in the sequence in each step. And then by expanding start symbol several times, we arrive at this sequence, let var id equals something. Then this red part becomes a nested candidate. And then one step more. Here we expand exp to fnid double arrow exp. Then this exp, this part exp, is a nested candidate and also a simple candidate. Okay, then we have constructed two algorithms. One to compute simple candidates, another to compute nested candidates. The algorithm for simple candidates computes all simple candidates, and actually there are a finite number of simple candidates. And in general, there may be infinitely many nested candidates. So let's see an example. So in the previous case, there were only two nested candidates, but in general, there may be infinitely many. Then let's see by the arithmetic language again. Then the same program again. Then in this case, there are infinitely many nested candidates actually. And the infinitely many nested candidates can be captured by this graph structure. I don't explain in detail, but starting from this point, the path to the circle position are the nested candidates. So in general, we have to choose some suitable finite subset of candidates by some heuristics in implementation. Then, okay, this is implementation. We have used a tool called YAPB, yet another parser builder, which was recently developed by Kwanghoon Choi, the second author, and his colleagues. It was published in 2020. Given a grammar, this tool builds an error parser that can access the internal information of the parser. And we employed a cycle detection heuristic to avoid generating infinitely many nested candidates. And we have implemented syntax completion as an Emacs mode by using Emacs Lisp and Haskell language by using the YAPB tool. YAPB generates a parser from the grammar of the target language like arithmetic one or standard ML to parse up to the cursor and computes candidates, nested or simple candidates. When typing the tab key, Emacs Lisp program and Haskell program communicate via TCP/IP. So when the user types a tab key, Emacs sends program text up to the cursor and location of the cursor, and Haskell program computes the candidates and send back them to Emacs, which are popped up. Then I show some demonstration now. I execute the Haskell program, and then I show the Emacs.
We can't see your Haskell program. I think you need to share a different window.
Oh, sorry. Now I shared the screen, whole screen. So
Yeah, it looks better, yeah.
By typing tab key, one simple candidate is popped up, in this case, EXP, corresponds to EXP. And let's see, nested one. Then EXP and EXP in, EXP end was popped up. And let's see, arithmetic one. Let's see, arithmetic one. Then this one is nested version, and this is the simple version. Okay, let's come back to the slide. There are many related work, and I present some of them. In 2016, Amorim and others presented some tool. They present incomplete program text using placeholders with placeholder inference. And incomplete program text is syntactically complete except for the placeholders. Users can select a placeholder for expressions or various syntactic component, and then syntactic candidates are popped up. In contrast, we do not use placeholders, so we allow arbitrary program text. And in 1998, LRC system I mentioned was presented, and unfortunately this is no longer available. I communicated with author. This one generates graphical language-oriented tools and takes a high-order attribute grammar and generates attribute evaluators. Generates editors as an instance. So users can edit the code but the editors with the syntax completion functionality have not yet been generated by LRC system. Although the authors insisted on it is simple to implement syntax completion. Another one was by ourselves. In this work, we took the approach of grammar transformation. But the grammar transformation was done manually, although the algorithm was given. And there should be some relationship between the current study and this one. Future work. One is to use our tool for the real world program language and to give a proof about the algorithm conforming to the specification, and to incorporate the identifier completion into the tool. This is a little bit complex, but it's possible, we think. And attribute grammar may be suitable for uniformly achieving syntax and identifier completion, and argue the time complexity for nested candidates. Thank you.
Thank you. So any questions? Well, I have one while we wait for others to see. So you said that you don't consider what is after the cursor, but let's take one of your first examples with the free open brackets with function applications, where you suggest either 1, 2, or 3 closing parentheses as this. But if we assume that after the, yes, exactly this one, if you assume that after the cursor there is 1 parenthesis, couldn't you use that to exclude the last of the possibilities? Because if you actually add 3 closing parentheses, then given that there's already 1, you would get too many closing parentheses.
Yeah, so we'd like to consider that point. So we like to utilize the already input symbols after the cursor. It is much better. But currently, for the simplicity, we just look at the symbols up to the cursor.
Yeah, let's see that nobody else has marked wanted to ask questions, so I can ask another one. So you said that in one of your examples with the FN arrow, there was expression was the next one, and you marked that as just a ... But an expression can start with different symbols, so either a number or a variable or an open parenthesis and things like that. So couldn't you suggest these as possibilities for what comes next, rather than just leaving it empty with ... Yeah, there.
Sorry, I didn't capture the question. Sorry.
Yeah, so let's assume that you didn't have the Y in the last line, the last Y, so you just have the arrow. Then what you would suggest from that would be just ...
So like this one.
Yes, then your suggestions would, yeah, the simple suggestion would just be ... But it's also possible to suggest the possible ways an expression can start.
Yeah, so in this case, just ... So,
yeah. So using the set of starting symbols for the non-terminals as suggestions, possibly. Have you considered that?
Yeah, we have considered about many possibilities, and we considered we reach the current specification. So providing the starting symbols may complicate at the current status.
Yeah. Okay, thank you. Let's see, any other questions? Doesn't look that way, so let's thank the speaker. And this is the end of this session, and the next session will start in half an hour using a different Zoom room than this, but we'll leave this Zoom room up so you can use it to chat to each other during the break here in the next half hour. But remember that you need to join a different Zoom room for the next session at 11:30. Yeah, so have a nice